Is for exoplanet outreach, and I think most of you listening to this are astronomy enthusiasts, right? And some might be already in the field. So you may feel that this is little basic or little like very basic stuff, but considering other people, I don't want them to be left out. After all, this is an outreach to exoplanets. And I suggest that if any of you have questions in between, just write them in comments. I can address that at the end of the presentation. If not, you can take a note of your question and we can discuss at the end, okay? And first of all, I thank each and every one of you to be here, connected virtually in different time zones, I believe. I'm really, really glad about it, okay? So this presentation is going to be a general one, starting with how big the space is, followed by an introduction to exoplanets and their detection methods. And I will talk about the exciting part, characterizing its nature, its atmosphere, and finally show you some of the interesting exoplanet details and some recent discoveries. Okay. Of course, we all know that the space is pretty big. In this video, you will see some comparing the huge stellar objects, and you're about to witness how small and negligible we are. I'm sorry. Okay. The, as you as you have seen in this video, there is there isn't just one star present in our galaxy. There are like millions of stars out there, and Proxima Centauri is one of the nearest stars. And here, as you can see, it's the Earth is almost very, very small when compared to the sun itself. And at least there are thousands of solar systems present. And in this case, what are the possibilities for the existence of other worlds or planets? A lot indeed. And now that you have known that there are other planets outside our solar system rotating a different star, we call them as extrasolar planets or simply exoplanets. But does every exoplanet have the same characteristics? Hmm, well, life is not that easier, you know. In fact, there are way different than what we have in our own solar system. Like in ours, we have four terrestrial planets and the remaining gas giants. But the exoplanets are separated into four different major kinds. The first is the terrestrial. They are considered to be the terrestrial exoplanet if its size is between half of Earth size to twice its radius, or even more smaller. The famous of this kind is the TRAPPIST-1e, which is present in the habitable zone, which means that this exoplanet is in a suitable region from its star to hold life. And the second type is the gas giants. They are similar to our Jupiter, that they are mostly composed of hydrogen and helium, and there are subdivisions in this kind, like hot or warm Jupiter or ultra hot Jupiter. An interesting thing about this exoplanet is that, unlike our Jupiter, that form beyond the snow line, these hot Jupiters orbit their host star very close, less than the one astronomical unit approximately. It's like imagine a hot Jupiter in a place of Mercury or Venus. It's that close. And the next kind is the Neptunian. They are like our Neptune and Uranus, hydrogen and helium dominated atmosphere with a rocky core in it, and also sometimes there will be heavier metal core. And the last and super kinds are the super Earths. We have a lot of super Earths in our galaxy with a size twice as Earth's and up to 10 times its mass. It's pretty huge. It can be a pretty big world like Earth if it's in the habitable zone. So we have discussed all these different kinds of exoplanets, but how do astronomers detect them all? Well, through a telescope, of course, yes. We have a lot of ground-based and space-based telescopes, but what are the methods? There are like different methods through which we can detect these exoplanets. In this session, I'm going to talk about just one method which almost many telescopes use it, and that is the transit method. Why? Because they provide very accurate measurements on their physical parameters like the system radius, like both the planets and the Earth, sorry, the planet and the star, their orbital inclination from the point of view whether the system is present in the 180 degrees or is it inclined a bit, like is it 270 degrees inclined, such kind of information. And the transit timing measurement. How long does the planet take to cross the star? That's the transit timing. And finally, the stellar density. And the main thing is that this method can allow for the planet's atmosphere to be studied through something called transmission spectroscopy. So what it means is that imagine this to be the telescope with the spectrometer. And when the light from the star, it passes through the planet's atmosphere, the resulting spectra can provide details about the chemical compositions in the planet atmosphere. And here is a transit that I was telling. This is a star and this is the planet. And we astronomers, we initially focus the telescope on the star and calculate its brightness so that when we observe a planet that is passing by the star, its brightness, its intensity will start to reduce, indicating that there is something crossing the star. What possibly could it be is an exoplanet. So this is the transit method. So eventually, our next step is to characterize the atmosphere. And why is it necessary to characterize the atmosphere? We are some curious people, aren't we? Like cats. At first, we didn't know that there are other worlds present apart from the ones in our solar system. And when we knew that there are millions of stars present, we started to think if there are other stars just like our sun, there should also be planets orbiting them. At least some system that should have some planets like we have in our solar system. And we detected the first exoplanet in 1992. Now that we have detected the different kinds of exoplanets, over 5,000, we need to characterize each one of those kinds and know what they are composed of. How? Like I earlier said, using a transmission spectra. In general, the transmission spectra of an exoplanet looks like this. This is a clear model spectrum of a planet TRES 4b. The reason why I'm showing you this is because not every planet has a clear atmosphere. Even in Earth, we have clouds. Similarly, there are clouds and hazes present in the exoplanets as well. Exoplanets, especially the hot Jupiter classes, they tend to have clouds because because of the irradiated atmosphere, and it's mainly because they are very close to their host star. Remember the gas giants which I told earlier? And as you can see here, this is the cloudy model spectrum of the same TRES 4b. When you compare these two model spectrums, you can see that these features over here are diminished, and these are because of the presence of clouds. So when we look at the model spectrum that is very cloudy, the features are even more diminished. And here, to talk about the wavelengths, this is the optical region, and this is the near infrared region, and the remaining or the mid infrared region. And in this case, here in the mid infrared region, you can spot some features. Here is the silicate cloud species. And this is another reason why we astronomers are craving for powerful telescopes. If an exoplanet is very cloudy, we study the spectrum at a very longer wavelength, like near infrared or mid infrared, and study about their clouds that is present in the exoplanetary atmospheres. For example, the recent JWST and the famous HST, the Hubble Space Telescope, can do this job very well. It gives precise results about what kind of cloud species does the exoplanet have. And speaking of habitability, in a spectrum like this, we look for biosignature gases like oxygen, methane, carbon dioxide, water, and even phosphine. However, methane or oxygen by themselves would not make a reliable biosignature. But these molecules together, that is methane and oxygen together, would result in a production of carbon dioxide and water. This will be the case for the exoplanet with temperature similar to our Earth. For the habitable exoplanet in the habitable zone, the terrestrial kind. Now to the wonderful part of the presentation. I am going to show you some of the exciting words. The first of the list is the TRAPPIST-1 system. This is similar to our solar system. There are 7 exoplanets and the star is a red dwarf. It's very, very small compared to the sun. And if you look at the TRAPPIST-1 system compared to our solar system, well, it's pretty congested, as you can see. But the interesting part is that there are 4 exoplanets, D, E, F, G, or within the zone, they are in the habitable zone of the system, which means that it can hold life. And if you look at the transmission spectrum of these exoplanets, we can find the water feature at 1.4 microns. This is a common feature which we can find in many exoplanets. But this doesn't mean that this exoplanet is habitable. Remember, we are only talking about the atmosphere. Its surface is still unknown. We don't have any powerful telescopes that can view the surface directly. Well, if we want to talk about the habitability in clouds, Venus could be the best example because there is a debate going on that there is a phosphine signature in the clouds of Venus that can be habitable in the clouds of Venus, but we need technology to live in the clouds of Venus, right? So moving on to the next. The next is a very strange planet. It's called WASP 76b. We can call it as Hell Planet. The temperature during the day in this planet is approximately 2,400 degrees Celsius. We will be fried humans at this temperature. Or I don't think that anything reminds if we visit this planet, not even our bones, I guess. It is pretty hot, but that's not the reason why it's called as Hell Planet. Because of their high temperature, the iron molecules present in the atmosphere evaporates, forming metallic clouds. These clouds then taken by the strong wind at the speed of 1600 kilometers per hour to the other side of the planet, and it causes rain, like an iron rain. Trust me, you don't want to visit this planet. And the next is this. It's called HD 1897-33b. This looks beautiful, isn't it? It looks just like Earth, but it might resemble Earth, but it's not as nice as Earth. This is why we call this as Earth's evil twin. It's a hot Jupiter gas giant, and the blue color in this image, it is thought to come from the silicate particles in the atmosphere. As a result, it rains silicate glasses like the iron rain. Here in this planet, it's a silicate glasses. That too because of the wind speed that approximately 4,300 miles per hour. The rains will be sideways. That's even more worse, I guess. And following is the darkest planet ever discovered. It's called TRES 2b. Astronomers calculated that less than 1% of the sunlight is falling on it. And they proposed a theory that it could be because of the light absorbing chemicals present in the planet's atmosphere. It could be something that we haven't seen or discovered yet. It's like a mystery particle. And finally, this presentation won't fulfill if I don't talk about the recent discoveries from the Webb's telescope, right? WASP 39b. Two interesting results were found. The first is that carbon dioxide and a lot of water feature are found in the atmosphere. Here in the transmission spectrum, as you can see, there is a carbon dioxide feature and a lot of evident water feature here. But when the astronomers started to work on the data, they started to see the small bump over here. They were surprised because all these CO2 abundance, water abundance, it was expected. But this one, they weren't sure what this could be. And then later it was found that a special thing, like they found a photochemical molecule, sulfur dioxide. This is the first time that the astronomers discovered such photochemical molecule. Because there is a lot of water molecule present in the atmosphere, the photons from the planet host star continuously interacted with the water molecule and forming sulfur dioxide. The thing is that, as I said earlier, they were expecting a common molecules like carbon dioxide, water, carbon monoxide, sodium, potassium, and stuffs. But with JWST, with the help of JWST, they were able to find a specific photochemical molecule. So this was just amazing. And they published five beautiful papers on this exoplanet. And we are almost near to the conclusion part. So soon, I know. So this image is from the Hubble Space Telescope. It's called the Deep Space Image. I hope you can see some blurred dots and big blobs. So each dot you see there is a galaxy. Now they discovered 5,000 exoplanets, which I was talking earlier about, is only from our galaxy. And we are still discovering more exoplanets. We still have a long way to go. If each dot you see in this image is a galaxy, then imagine how many exoplanets will be present in each one of them, and how many could be habitable just like our Earth. This is the reason why this image always makes me to wonder about the possibilities of so many beautiful, mysterious, and terrific things out there. And this is my another favorite image. This was taken by the Voyager 1 spacecraft when it was almost at the end of the solar system in 1990. This small dot over here is the Earth. It's the Earth. That's Earth. Whatever has happened, whatever is happening, and whatever will happen, it will take place in that small dot. Those are the beautiful sentences given by Carl Sagan, which you can read later. What I'm trying to convey from this image is that something that the Earth is big, but it's not. It is very small comparatively, of course, like the very first video which you have seen. And if you think we just have 100 years on this Earth to live, again, it's a very small number. Don't you think we should spend our life loving people than creating war and other heartbreaking stuffs? Come on. You know, it's very simple. Just live your life in a way that you don't hurt or harm other people, because I'm not trying to promote vandalism here in the name of living your life. Just remember that our Earth is big, but the space is enormous. We have a lot of discoveries to make, we have a lot of technologies to make, and we humans have to be united to face whatever's out there. Okay. And that's it, guys. Thank you so much for spending your time with me and listening to me with so much of patience. And I'm really sorry about the inconvenience that happened before. I am so sorry. Thank you all. If you have any doubts, if you have any questions, you can ask me. I'm open to your questions. I think, I think we should unmute the chats, I guess. Or do you have any, you can, I think you can raise your hand, I guess. Can you? Okay, we have to unmute RF. Mr. RF, I'm sorry. Okay, I'm sorry, just a minute. I think you can.
A great presentation, Anita. Well done. I'm an astronomy enthusiast as well. I work with your brother. So my name is Madhu. Hi. Great presentation. I mean, I've always been fascinated about all these exoplanets and all this space stuff and the space odyssey and other things. But just one question is: any improvements or anything being done on the warp drive or the antimatter? Anything progressed in those lines? Do you know? Because people have been um, experimenting on all those things, but I don't think they have got any further than the lab experiments. So do you know anything about the warp drive or antimatter?
By antimatter, you mean the dark matter, isn't it? Okay, so to my knowledge, I think that these stuffs are still theoretical, like you said. It's not yet proven or anything. It is still theoretical.
Okay, because the amount of space and the distance that's involved in reaching to even Alpha Centauri is 4.2 light years, which is, it's
Yes.
conventional rocket system will take 70,000 years to reach there. So that's not going to happen. So that's why I asked you this question.
That's right. If we are able to discover a wormhole or something like that, it will be much more convenient for us to explore the space, I guess.
Right, it comes in interstellar like that, but I don't know whether the wormhole concept is real, but I've seen that many times. But
yes, it is still theoretical, yes.
Yeah, those are my questions. Thanks a lot for your presentation. Very nice.
Thanks a lot for your participation. Any other questions, comments? Or if you cannot unmute yourself, you can just raise your hand. My host can unmute you. Camila.
Thank you, Anita, for the presentation. And don't worry for the things happens in the internet. Maybe it was because the meeting is public, and then
yes.
But the presentation was very interesting, and thank you very much.
Thank you. Thank you so much, Camila. SB.
Hi, Anita.
Hi.
Hi, your presentation is very nice.
Thank you.
I really enjoyed your presentation. And I have one small doubt, okay?
Okay.
The galaxy, you were talking about the temperatures, right?
Temperatures.
Some temperatures, exoplanets, the temperature is very high. When the temperature is very high, how actually you are finding what are the chemicals are available inside the exoplanet? Like you said, no, carbon dioxide, sulfur dioxide, all these chemicals are present over there. Those things and all, how actually people are finding those things?
It's a simple concept of spectroscopy. You know, we use prism to identify the different lights, you know, the lab experiments. We use the same concept in exoplanets as well, except
Okay.
our target is big and our telescope is also big. So it's just this: when we enter the light into the spectroscopy, of course it gives different filters, right?
Okay.
Each filter has the capability of observing different molecules and different atomic species. From that, we can say that, okay, here there is an absorption. It means that there is this molecule present in that atmosphere. And at this wavelength, there is an absorption. Okay, at this wavelength, which molecule can observe this light? Okay, it's carbon dioxide. So there is a carbon dioxide in the atmosphere. That's how we find it.
Wow. Okay. Very nice, Amma. Thank you.
Mhm. Thank you so much for listening. And do you have any other questions?
No. No. Carry on.
Okay. Yoga Priya.
Hello, your presentation was very good. Congratulations and thank you. And about the spectroscopy, we also use in medicine for like magnetic resonance, MRI scans to study the body, and also about the we have any tumors to detect it. And yeah, it was so interesting about it. As I know nothing about this, but I still like I felt like I traveled in. I like watched some Guardian of Galaxies movie, like exoplanets traveling through it. It was nice to know about these planets existing and this kind so many galaxies around us. It was very nice and congratulations and thank you.
I am happy that you understood, because most of you here are exoplanetary or astronomic enthusiasts. And I'm glad that I've made this presentation simple enough to, for you to understand in a simpler way than showing complicated graphs and stuffs like this. And an extra comment on this particular plot is that the data points are real. But earlier, which I showed you this, here it shows the model spectrums of this exoplanet. An additional comment to this is that we create models of the spectrums of a particular planet to confirm the observations we have done. Like we do experiments. First, we write a theory, and then we do experiments to confirm the theory. It's similar to that. Preparing a model spectrums are like theoretical part, and observations are the practical part in astronomy. Any other questions, comments? Doesn't matter whether it's silly or anything. I'll be happy to answer. Yes. Yeah. You can raise your hand if you have any questions. Okay, so I think we can finish it with this. So I really thank every one of you. I also owe you an apology for the matter what happened previously. And a special thanks to my host to take control of the presentation. A special thanks to you, Shanmugh. So meet you all in another presentation. Meet you all in another astronomy seminar. I hope that I can talk about this more if you're interested. So see you guys. Thank you so much for participating and being here with me. Thank you so much. Bye bye.